In this video, we're going to consider electric fields for continuous charge distributions. To do this first, we're going to start with our point charge solution and consider only an infinitesimal amount of charge. If we do that, the small electric field created by that infinitesimal charge is K dq, the amount of charge, divided by the distance squared from the charge to the location you're calculating the electric field, times the unit vector r hat, which is a unit vector pointing from the charge to the location you're looking for the electric field, just as before. Now what we're going to do with this is we're going to sum, or in the words of calculus, integrate the sum of all of these little charge contributions. So to do that, we simply write the integral as follows. The electric field, E, is equal to the sum of all charges of the small contributions of each electric field of each little bitty charge, which is the integral across all charges of K dq over r squared r hat. Now, fairly easy to write the integral, but to do the integral can be tricky, and here's the reason. dq and r appear to be different variables. They must be related. And we're going to have to find the equation that relates them, so there's only one integration variable. That could be x, it could be v, it could be a. It's going to be some spatial dimension in the problem, and everything else is going to have to be written in terms of that integration variable. Another problem is that r hat, and q are usually not constants and cannot be pulled outside the integral. So that means that we may have to write, for instance, r hat in terms of ijk, which are constant unit vectors and can be pulled out. But when you write the r hat in terms of ijk, that usually means you end up with trig functions, and so these tend to have trig functions inside of these integrals. These integrals can be challenging. This is part of the problem. We'll take a look later on at some other ways to attempt to attack the problem, rather than just straight head on. That's the purpose of later chapters. Now the basic steps to apply and solve this integral are first. First you got to set the integral up. So what we're going to do is break the object into a bunch of infinitesimal point charges dq. We're going to find the magnitude of the electric field for each infinitesimal point charge. That means we're going to find dq in terms of the integration variables. We're going to find r in terms of the integration variables. Now you don't have to find the magnitude. It's possible to just find dq and use r hat. That's a good way, especially in upper level classes. It's usually the best way. But for simpler problems, often in this course, you can just find the magnitude, and then in part 3, instead of finding r hat, which would be the alternative, you can just say, if I put a positive charge at the location I'm looking for the electric field at, which way is the force on a positive test charge? That means it'll either be r hat if it's repulsive, or it'll be minus r hat if it's attractive. And last, after you've done that, you'll need to integrate over all the charges to get the total electric field. I'll come back and show in a minute an example on how to do this to show the actual steps in practice, but I want to put this in your notes so at least you have it in one place so it can remind you what we're trying to do. Now in finding dq, there are two types of problems you're usually given. One problem is that you're given a uniform charge distribution, and the other is you're given a non-uniform charge distribution. All of these use what are called charge densities, which are very similar to mass densities you should have had in a Physics 1 course. So the linear charge density is defined as the derivative of charge with respect to the linear variable. In this case, I'll call that x. In mass charge densities, when we were talking, mass densities, when we were talking about linear mass densities, this was dm dx. Now we're talking not about mass but charge, so it's dq dx. If it's uniform, what that means is that it's constant. So lambda doesn't vary. It's a constant. And you can take any part of the project, find the charge, and divide by that length to do it. You could be, let's say you have a rod. It could be a third of the rod. You take the charge on a third rod divided by a third of the length of the rod. It could be half. But usually we take the whole rod. So it would be the total charge, Q, divided by the total length. This is always true. That's what the 3 bars mean definition. The second one is only true if it's a uniform distribution. For a surface area charge distribution, we're looking for sigma. And it's defined as the derivative of the charge with respect to an area. Again, for uniform distributions, it's a constant and it's Q over A. The total charge over the total surface area. And for volume, it's rho. That is the charge density or volume charge density. And it's the derivative of Q with respect to the volume, not the velocity, the volume. And that's equal to Q over the total volume, assuming again it's a uniform distribution. Now, if you've got a non-uniform distribution, things are a little different. In a non-uniform charge distribution, when we have to break it up into little pieces, each piece of charge will depend upon the linear density, for instance, at that part, times the width of the piece of the material that we're considering. This lambda will be different in different places, for instance, on the bar, if it's non-uniform. Or if we're looking across an area, this sigma will not be a constant. It will vary. These values, sigma, lambda, and rho, must be given to you. So they'll be given in the problem. They could say it is set up with a surface charge that goes as r squared cosine of theta. Or it could say that it's a linear charge density that goes as 3x squared. Then you know to put 3x squared in there. In these cases, you have to have that lambda, that sigma, or that rho, or you cannot work the problem. All right? These are less common at the lower level than are the uniform distributions. They are more common at upper level in real-world problems. All right. Now the next thing to do is actually to work a problem. And I will work a problem involving a bar, and I'll do that in the next video.